Welcome everybody. I've got everybody muted at the moment. We got a pretty good sized group. I'm going to unmute real briefly. I just want to make sure everybody can hear me all right. Can everybody hear me good?
Yes.
Great.
Yes.
Yep.
Okay, I'm going to mute everybody again. It's not that I don't want to hear from you. It's just we got a pretty good sized group, so I'm going to try and kind of manage the background noise. And then I welcome your questions, but where I've got you muted, we'll hold them to the end, and then I'll kind of have a Q&A session. So let's get started here. We're starting into this compressor fundamentals webinar. During these kind of goofy times with pandemic and everything, we wanted to find additional ways to kind of reach out and help our customers and our dealers in whatever ways we could. So we figured this may be one way that could help. This is a very 101 level, if you will, fundamentals for reciprocating compressors. So many of you this may be a repeat of information you may know, but the idea is we're trying to kind of help everybody. But there may be things that even you old dogs may get as well. So I'll move along here. A little introduction to myself and Hycomp. Hycomp's been in business since 1969, manufacturing oil-free recips. Since 1969, we started out in the air compressors, oil-free reciprocating air compressors, and have since added boosters, quote unquote, which are gas compressors. And so we have a line of gas compressors and air compressors. And our approach is somewhat unique in that we can really handle a lot of different scenarios with how our design operates. Brief background on me: I've been with Hycomp for 11 years. I started here in our engineering department. Don't hold that against me. And I have kind of worked in various roles here. I'm currently the account manager covering half the U.S. and a good chunk of our international business as well. And unfortunately, you get to see my ugly mug there. So the objectives of this is to give you a little better understanding of the function of reciprocating compressor, discuss some of the design considerations when we're specifying, and that, like I said, this is fairly high level. We'll talk about single stage versus two stage, single acting versus double acting, fairly basic stuff like that. We're not going to get into too in depth, at least in this webinar. We can address some more in depth concepts in further. This one thing I should probably mention is that we intend this to kind of be a webinar series, and so we have some additional things planned for the coming months. But if there's things that, if you have a hot burning, I really would like to know how this works or what this is within the industry, within reciprocating compressors, within how Hycomp does things, I would love to hear it. And we'll have, like I said, we'll have a Q&A session at the end, and we'll also get you my contact information as a follow-up to this webinar, so that you can get a hold of me or the other members of my sales team. So this is going to be a little wordy, but we're going to just briefly touch on some definitions related to compressors. So reciprocating compressor is a reciprocating compressor, or piston compressor is another name for it that you may hear, is a positive displacement compressor that uses pistons driven by a crankshaft to deliver gases at higher pressures, or at pressures higher than what they began at. Another term that you'll hear frequently is compression ratio. It is defined as the ratio of volume of gas before compression to the volume of gas after compression. So you'll hear something like this is a 3-to-1 ratio. And that's, there was 3 parts compressed into 1 part. Briefly touch on compressor capacity. There's a lot of numbers and units that get kind of thrown around here. The definition is it's the quantity of gas actually delivered by a compressor in a particular flow unit. And I touch on some of the more frequent ones. There's many more than this, but there's the one that we use the most here at Hycomp is SCFM, standard cubic feet per minute. And that's somewhat self-explanatory, but it's cubic feet per minute, and then it's referenced back to standard conditions. Another one you see quite a bit is normal meters cubed per hour. That's a similar concept of flow, but it's cubic meters and then per hour, and then it's referenced back to normal conditions, which is similar to standard conditions, but a little bit different. And that's tied back to the metric system. Another one you'll hear just plain CFM or ACFM. ACFM is really kind of a better term because it's less confusing. When you hear somebody say CFM, is it SCFM, is it ACFM, is it ICFM? So ACFM is actual cubic feet per minute. One thing you have to remember when you're talking about that, you need to talk about when you say I need X amount of ACFM, you also need to qualify that with the pressure at which you're talking. So sometimes you'll be talking, I need 10 ACFM at the inlet, which will lead into our next definition, or you say, I need 10 actual cubic feet to this particular machine, so that would be at discharge conditions. ICFM is a similar, as I mentioned, is a similar unit. You see that a lot in air compressors. And so in the context of an air compressor, an inlet cubic feet is the cubic feet entering the compressor at inlet conditions, which frequently is fairly similar to SCFM, but as you get into higher elevations, that may diverge a little bit. The next definition you'll hear, we'll talk a little bit, use this term a couple times throughout this presentation, is swept volume. This is a reciprocating compressor term, and it's the volume displaced or swept by the piston when it moves between top dead center and bottom dead center. Briefly, we're going to kind of put our recips in context of where it fits within compressors. There's two main categories of compression. There's positive displacement, which are operated by trapping a specific volume of air or gas and forcing it into a smaller volume. So two basic examples of a positive displacement are rotary compressors. As those loads, you have a volume and then the loads come closer together towards the end of the end, and that's what creates the compression. And then as we've talked about reciprocating, which we're going to go into more in depth. And then there's centrifugal type, which operate by accelerating the air and converting the energy to pressure. And two basic designs of that are a centrifugal and an axial. Both work in somewhat of a similar, in that they're spinning at a relatively high RPM, and then that high RPM and the shape of their vanes, there's quite a few design considerations, and we're not going to really get into those too deep, but that's what generates compression. So we're going to dive a little deeper here into reciprocating compressors. In a reciprocating compressor, a volume of air, and I do have some graphics on this next, they're fairly large graphics, so it's on the next slide, but remember this, and then we'll talk about it on the next couple slides in the graphics. So in a reciprocating compressor, a volume of air is drawn into a cylinder, is then trapped, and then is compressed by a piston. The piston then goes up toward reducing that volume, and that eventually leaves that cylinder into the discharge line. The way that trapping occurs is the cylinder valves control the flow of the air through the cylinder. These act as check valves or one-way valves. So you'll have a valve on the inlet side and a valve on the discharge side that operate one way opposite of each other. There's a couple different types of reciprocating compressors. There's a single acting. Single acting is when that compression event happens when the piston goes towards one direction. Most of the time that's towards the head and away from the crankshaft. And then there's a double acting compressor where that compression event happens in both directions. So on the upstroke, you're compressing towards the head end, and on the downstroke, you're compressing towards the crank end. And there's some advantages to double acting a compressor, and there's some physical design considerations that sometimes are a disadvantage when you're talking a smaller compressor. So here's our diagram. Let me see if I can get a drawing tool here and make a little, so as that piston goes down, we draw gas in through this suction line, and this representation of the suction valve, it draws open based on the differential. That piston then drops down, and we fill this volume with gas, and then as the crank reverses and we go to our, goes to the other side of the crank, I should say. That piston then goes back up towards the head, and this volume from here is then pushed and squeeze this volume into this smaller volume, at which point that discharge valve opens and our gas leaves at a higher pressure. There's some important parts that this diagram is kind of pointing out. We have our piston. Our piston's an important part of that. Our rings are also an important part of that. You need something that allows that volume to be sealed against that cylinder wall, so that if it isn't, then you're just blowing some gas around everywhere that you don't want it. See if I can clear off our drawings there, and we'll move on to our next slide. So this is, as I already discussed, but these are kind of some graphics of that. Suction valve is open as that piston's going down. One thing to point out, the pressure of the air in the cylinder is equal to the suction pressure, this blue. So this is all basically the same pressure. And then as that piston starts to come up, that pressure inside the cylinder will elevate slightly, which will then close that suction valve. And then at another point, that it will rise enough that it opens that discharge valve. And then we were pushing that compressed gas at the higher pressure into the discharge side. One effect of compression is it does generate heat, and that's caused from the actual compression. As you're adding energy to compress that, there's also energy that leaves the gas as it goes down, and that energy shows up in the form of heat. Heat becomes an important design consideration in any compressor, and I bring that up now because it leads into some of the next concepts we're going to talk about. So this is a little similar diagram. That cylinder we just saw is now laid on its side, and this is what's called a pressure volume diagram. We're not going to get super in depth into the PV diagram, but it is kind of a nice little graphical way of thinking about how that works. So this is showing the distance that cylinder travels, and then it's showing these 1, 2, 3, 4 are events throughout the stroke. So 1 is as our piston's going down, that's where our suction valve opens. And this graph is also depicting volume. Let me get a drawing tool for you, sorry. Volume on this direction of it, and then we have this PS and PD, that's pressure suction, pressure discharge. So this is pressure in this direction. So as that cylinder moves down, we're seeing that this on the graph is our pressure, and at which point, at point 1, our suction valve is open and we're intaking gas at the suction pressure. Then at point 2 is when our piston begins to go back up. We're hitting the other 180 degrees of that crankshaft. And so we're depicting this pressure rising up until point 3. Point 3 is where our discharge valve has now opened, and we are pushing gas out, and also the pressure still elevating. And so this diagram is something that can be used. Like I said, we can go you can go much more in depth on pressure volume diagrams. They can be used for troubleshooting if you have the real time to monitor and draw a PV diagram. But it's an easy. I like to use it even at this fundamentals level, just to show how each stroke works. To me, it's a good way to see it. Get rid of these drawings, sorry. So now we'll move into what a two-stage compressor is. So actually, I'm gonna back up for a second. One issue is if you say you're going to put a huge amount of compression ratio on this this particular cylinder, what happens is these points move further down. So if you're, say, we'll say something radical, we're going to go from 10 psi to 1,000 psi in one cylinder. And so what would happen is this point 1 would move somewhere, way down here, because it would take a long time for that pressure to equalize back out to get that lower pressure in if the pressure was at 1,000 prior to that. So then that point drops way down. Point 2 remains the same, but then point 3 to get it all the way up, because our PD over here would actually be way up here or something like that. So our point 3 then is very narrow, and our point between 3 and 4, where we're actually flowing gas out, becomes very narrow. And so and then also you'll generate a huge amount of heat doing all that compression all at once. So the way to get around that and to work around that is to do a multi-stage configuration where we do that same kind of thing. We run gas into our first stage cylinder, compress it, and run it back out. But then we do that in a set approach. So we'll go back to our 10 to 1,000 scenario. We would do something where we go from 10 to, say, 150 psi. That's a relatively doable. And these are all, I'm just spitballing numbers. So we would do that, and then we would have an intercooler here, and we would get rid of that heat that we needed to deal with. And then rather than going from 10 to 1,000, we're now going from 150 to 1,000 here on our second stage. That second stage diameter should be smaller because we already reduced the volume once, and so we need to continue to reduce the volume. Otherwise, we just re-expand if we try to use the same size cylinder. And so there's efficiency gains, as I talked about. You get it allows your valves to operate within normal reason. You get rid of some of that temperature in between, so that you're not dealing with such high temperatures, which allows for selection of more standard materials, and many things. That's why a lot of times, and so sometimes, you may talk to us and we'll go, hey, I think that's probably going to take 3 stages, or that may take 4 stages, depending on what the compression ratio is. So kind of recapping the advantages of multi-staging, there's a reduction in power required to drive the compressor. That's due to those increased valve efficiencies. We're not spending a bunch of time filling a cylinder and compressing without leaving the cylinder. It allows for a better mechanical balance across the unit. Increase in volumetric efficiency, that's what I was talking about, where it takes a long time for that valve to open and a long time on the suction and a long time for the discharge valve to open. The sooner those open, the higher your volumetric efficiency is. Volumetric efficiency is, the definition is how much volume you get out of the cylinder relative to how much volume you put into the cylinder. There's always going to be a little bit of loss because you have the distance between the cylinder and the head and things like that. As I mentioned, lighter cylinders can be used, more standard materials, and it controls the operating temperatures. So now we'll just briefly kind of put those principles and things we learned and show a little bit how they are on a Hycomp compressor. Hycomp compressors, one thing I'll point out, are oil-free in design, meaning that we do perform the compression without oil. We do, however, oil lubricate our lower end. So we have me get my pen, sorry. We have this area here, which has oil lubrication. And one of the portions of the design that are important in the oil-free design is we use these, and it's a little tough to see, but we use these rings. And I mentioned before that those rings are important to the whole performing compression. And they're an important part in performing compression oil-free. So we use they're a soft good polymer, which we select based on what particular gas we're running. And so an important part for those is they don't withstand any of the side thrust that can occur from a piston that's directly connected to a crankshaft. So we have this extra area that allows those pistons to connect to these, what we call our guide pistons or crosshead pistons, which allows for a only up and down reciprocating motion. So by doing that, we create this little bit longer design, but it allows us to lubricate some of these important parts and then not lubricate the other parts, which gives you the longevity of oil lubrication and the cleanliness and lack of impurities in the gas stream. I'll kind of point out, just kind of put into practice some of what we just talked about and learned. We have our pistons here, as I talked about. I circled these are our rings. Our valves are here in the top. There's valves kind of behind here, just the way that this cutaway is, you can't particularly see them. And then we also have our piston rods. These gas packings seal that piston rod that's at above this area is at pressure, and below this area is at atmospheric pressure. So that's what those are doing. We have these, as I mentioned before, crosshead pistons. Our crankshaft is here, and our connecting rods are here. So there's portions of it that should be very familiar to anybody that's familiar with reciprocating or familiar with engines. And then there's the parts further up that are a little divergent from what you may be used to, but are important in the oil-free design. And then we'll kind of move on to the Q&A. One thing I'll mention before our Q&A, one thing that we've done, just to kind of mesh in with this doing compressor fundamentals, we have added some, and this is kind of a sneak preview. I don't think it's quite live yet, but we've added some tools to our website. I'll make sure that's showing up on the screen. But just allow you to do some of those basic functions: temperature conversion, pressure conversion, power, flows, and then we are including a calculator that allows you to calculate a couple different ways based on how flow rate, based on how quickly you can fill up a volume. So I just wanted to mention that as kind of a sneak peek. We'll kind of forward a link out to this when it's live. It's nearly live, but I don't think it's quite there yet, but I wanted to show you at least. So now I'm gonna kind of mute everybody. And if you have questions, by all means, after this, once we wrap questions, you'll see an email from us probably sometime today, thanking you for attending. And it'll have our contact information. If there's questions that you didn't get answered here, or if you didn't, if you felt it was going to take longer, or if you think of it after, please get a hold of me. I'm happy to answer questions. I'm happy to talk anything with you. So I'm going to unmute everybody. If you have questions, let's talk about them. See if they're unmuted.
Yeah, hi. Question. Are all dual piston reciprocating compressors two-stage?
Okay.
Hello?
Sorry, can you repeat it? I got about the second half of it.
are all dual piston reciprocating compressors two-stage?
Good question. No, there you can have many of our we have some units that are single stage that are just a single piston. But many of our single stage units are a dual piston. And the way that works is you have two pistons of the same diameter, and then they're connected to the crankshaft 180 degrees opposed. So when one piston's compressing, the other one's filling, and vice versa. But because they're the same diameter, the compression ratio remains the same on them.
Okay,
Does that
thank
answer
you.
your question? Any other questions?
Nothing yet.
Okay, well, if you do have further questions that you think of later, please feel free to get a hold of me. Shoot me an email. My email's up there on the screen. As like I said, I will we'll get a follow-up thank you email out that will have my contact information on there as well. And I appreciate everybody's time. I realize I'm setting a webinar can be productive or cannot be productive. I hope this was productive and informative for you. And I thank you.